analyze the data, and also communicate the insights with others. So that's really the exploratory. Okay, so let's get started. The online seminar, the exploratory online seminar number 51. Today, I like to discuss about machine learning, variable importance. Okay, and then here's the agenda. And we have like a bunch of stuff. So let's get started. So the prediction model. So it's really, when we talk about machine learning or even like statistical learning, it's really about this prediction model. So what this prediction model is, let's say that we have the data, and then that data have answers. Let's say numerical values or labels, for maybe like a sales or customer conversion or employee attrition, or that types of things. And then that whatever the data is, but we are interested in like the sales numbers, amount, how it increase or decrease, that kind of stuff. And then we use the algorithms to detect the relationship and patterns in that data that can be used to identify the answers, and then model those relationship and patterns are in the form of formula or rules. Then once we build a model, then we can use the model to predict the answers for the data that doesn't have the answers. Okay, so what that really means, so let's say like you go with use case. So let's say like we know who converted as paid customers and also who didn't convert in the past, right? And then like, we have customer attribute data such as, let's say like age or location or what type of industries they're coming from, and so on. And then we use the data, then we want to predict which of the current lead customers, so like the customers that are considering of maybe converting or not converting, but those customers we call it lead customers. So we want to predict which of the lead customers will convert or not. So this kind of case, like we want to build a prediction model that I was talking about. So if I draw the diagram, let's say like building a prediction model is like you have the data, right, like a left-hand side, and then you have the target variable, in this case, a conversion. So each row is the customer, and then customer converted, in that case, true, no converted, in that case, false. And then we have a customer attribute information like age, and time is the amount of time that we spend over the phone or something like that, and the country and so on. And then we use some kind of algorithms or machine learning algorithm or statistical learning algorithm to build up model. And then this model is really the definition of the pattern or relationship that algorithm can find the data that can be used to identify the true or false in this particular case. And then you have the data that doesn't have the answers. So like conversion column has like, let's say an A or null. And then you pass this data to the model, and the model apply the whatever the definition of the pattern in the past data. And then based on, let's say in this case, age or time or country or something like that, to predict, hey, this particular customer might convert, this particular customer might not convert, that kind of stuff. So that's the result that you are going to get. Okay. And then so there is a brilliant British statistician called George Box, and then he made a lot of great, useful comments in the past. And then one of the things he said was all models are wrong, but some are useful. And I think this is really important, and it's very deep, at least to me, because all the models, the moment you create the models are actually far from the reality, right? Like in this real world we live is very complex. There are a lot of things happening and it's changing. But the model is really sort of like approximation of the real world. More blunt way of saying it is like a kind of simplified version of the real world. So therefore, of course, it's wrong for compared to the real world. So if you're really depending on, sort of building the prediction model to predict the future, then, you're not going to get, you might get disappointed because in terms of the predictions wise, you're not going to be able to predict 100% of the time, or with 100% accuracy or anything like that. But the model has actually captured the patterns and then the relationship in data. So therefore, you can actually use that model not only for predicting itself, but also learn about what the model can have found from the data. So let's say, for example, like, which variables have stronger relationship. When I say variable in a table data, right, like Excel or spreadsheet kind of data, the column is typically the variable, something that changes. But which variables have stronger relationship with the target variable? If you're interested in like who, which customer is going to convert or not convert, then like maybe like age is more important, or maybe like a country has a lot to say, that kind of stuff. And how, if there are relationship, then how are they related? What kind of relationship? One increase and just one increase, or one increase or just one decrease? How much? And if the relationship are those relationships significant or kind of sort of like a reproducible um, relationship, right? So it just happened to be in the particular data set, in a particular, just a little amount of the change or something like that, that maybe like it's not worth to investigate further. And then what is the quality if we use this model to predict the future? And then can we really rely on it? It's like 80% of the accuracy, 80% of the quality of this prediction model compared to maybe like 20% of the quality of the prediction. So those are the things we can learn from the prediction model. Then next topic is analytics grammar. So we want to build a prediction model, right? But which algorithm we should use? And this answer is super complicated because there's so many algorithms in the world, and this is not academia. So like I'm not going to go into like a formal introduction of all the algorithms, but in general, and then I pick up most sort of like a common popular algorithms, aka the algorithm we support in Exploratory. But I think it's important thing is that the most important thing is like what is your target variable's data type? If the data type is numeric, let's say like you want to predict like a sales amount, right? That's actually a number or the numeric. Then in that case, you have the option of a linear regression model or random forest, XGBoost, and decision tree, and so on. But in that category, it's called like a regression model. But there are two types. One is a statistical learning model, and the other one is machine learning model. It depends people like who you ask. Like some people say like all of them are machine learning. Right. And some people say like, oh, this is statistical learning, machine learning kind of stuff. So it's the definition is always like not as important as we hope to be, but it helps us to sort of like see the difference between two type of algorithms. I'm going to talk about that a little bit later. And then the same thing for data type is a true or false. In this case, that kind of data type is called logical data type. Okay, so that can have only two types of values, true or false. Okay, can be yes or no, or 0, 1 type of nature of the data. Then statistical learning model, machine learning model. Statistical side, there's a logistic regression. And then there are others as well, but I think it's most common algorithm is logistic regression. And then the machine learning side, the random forest and XGBoost. The same thing with actually numeric. And then we call it like a classification model in this particular case that to predict the true or false. And the other data type is similar to true and false, but it depends on the time when you ask the question, the true or false can change. So imagine like if you're trying to predict if this customer is going to cancel that subscription, and then maybe in 3 months, this person might cancel, or maybe this person didn't cancel in 3 months, but 6 months later might cancel, or 12 months later might cancel. So depends which timing you ask, and then the answer is true or false is different. So the time component is important in that kind of case. And then that's called survival model or survival analysis. Okay, so in that category, we have the statistical side and the machine learning side. Statistical side, the Cox regression. Machine learning side, the survival random forest. Okay, so these are again is a sort of common or popular algorithm, but that doesn't mean these cover all the algorithms or anything like that. I'm sure like you might know like some other algorithms and stuff, but this is kind of give you the kind of a brief summary of like what type of algorithm we are talking about to build a prediction model based on the data type. Okay, and then the thing gets complicated is that each model or each algorithm gives you the different type of output. So when you build a model, and you can gain a lot of insights from each model, but depends which algorithm you use, then you get a different output, right? Or different. Try to convey the what the model finds, which is basically the patterns and then the relationship, but you get different output. So that makes you confused. So it turned out like you have to learn every single algorithms, and then that's super confusing. So, but when you think about it, the main difference among the various prediction models, the various algorithms, is what kind of patterns they could capture in the data. Okay, so for example, the linear regression model, which is, as the name indicates, it can capture the linear relationship between the variables, as opposed to the random forest kind of machine learning model can capture not just a linear, but it can be non-linear. So for example, like age and salary or something like that. And then like this company, like the salary doesn't increase as age increase in a kind of a linear way. It jumps when you get 30 years old, and then maybe like after 50 years old, it decreases or something like that. So that kind of relationship. So depends on the algorithm you use, it can capture different type of the patterns. In the data. So then we want to find out what patterns of the relationship in the data the algorithms have found. And that's the key sort of like meal that like we're interested in. So therefore, regardless of which algorithm we use, can we have a standard framework to understand the such patterns? We just want to know like what patterns, what relationship that we can find from this data or a given data. So that's where like analytics grammar comes in. Okay, so the analytics grammar is really a common framework for understanding the patterns and the relationship in data. And then regardless of which algorithm you use, like we just want to focus on that piece of information. So then we have this like a kind of four. I mean, because we say grammar, right? So like we have like four sort of like a different way of looking at it. So first, variable importance, and a prediction by variable, coefficient, and evaluation. And that's how we design the exploratory's analytics view. So when you go to analytics view and build a model, these are the things that you always see regardless of which prediction model you use. The variable importance is which variables are more important in order to predict the target variable. Let's say target variables again is a customer conversion or something. And then like which variables, let's say like age is more important, country is more important, industry is more important, or the time of how many minutes we spend over the phone is more important. And if Okay, so that kind of information that we want to know. And the next thing is the prediction by variable. So a given variable change, let's say like age change, and what is the probability, like how the probability changes in terms of conversion. Or if we're trying to predict, salary or something, then when the age change, like how much the salary would change. So those are the things that we want to know, and we want to know that for each predictor variable, in this case, each attribute, employee attribute or customer attribute, and so on. And then the third is coefficient. This coefficient is available only for statistical learning model, not the machine learning model like random forest or XGBoost. But what it is like how much does a target value change, target variable's value change, salary, for example, change as 1 point value changes in a given predictor variable. Meaning, like let's say like you have the age as a predictor variable. And then like when the age 1 point change, meaning 1 year change, 1 year increase in the age, how much of the salary increase or even decrease that we can expect in salary. So that's the really the coefficient about. But also more important thing, I'm not sure. I shouldn't say like more or less kind of stuff. All are important. However, this key piece is actually really useful. Is that change is statistically significant. more bluntly say, it's like a two variable, right? So let's say like salary and age relationship you're trying to investigate. The relationship between them is really significant, or maybe something that it's not worth being serious about. So those are the things you can find under the coefficient. And then the last not least is the evaluation. Evaluation has two types. One is a prediction quality. That's like sort of like intuitively, like we want to know, like you create a prediction model, how reliable this prediction model is. But the other piece of the evaluation is a statistical significance. And as the name suggests, this one is available only for statistical learning model, not for the machine learning model. But statistical significance evaluation is really the model you build, and then like, you want to know the relationship, like sort of like this model and the target variable can be salary, can be conversion, can be cancellation, whatever. And it might be able to explain like who's going to convert, who's not going to convert, but maybe like not much. It's not really something that this model might look like explaining, but it's not really statistical significant, meaning it's not really reproducible. Maybe this particular data can be explained just a little bit, but not much kind of stuff. So those are the things that we can do under the evaluation. And then like I draw the whole pictures here. Again, at the top is the data type of the target variable. So like a numeric true, false, and time, right? And then that means the numeric is a regression model. The true, false is a classification model. The true, false, and time is a survival model. And then in each category, there's a statistical side, which is green, and a machine learning side, which is purple. And then each section inside the box, it says variable importance, prediction by variable, and then there's the coefficient evaluation. Those are the grammar. So what I'm trying to say here is like regardless of which algorithm you choose, you always have similar sort of like interface that helps you understand what the model has captured. Okay, so then today's topic is really focusing on this variable importance. Okay, so the variable importance is really about which variables have stronger importance with the target variable or stronger relationship with the target variable. Okay, then how we calculate this variable importance, right? So how or even model calculate this variable importance. So first, you build a model after removing one of the predictor variable and variables, and evaluate how much the quality of the model degrade compared to the model with all the predictor variables. So these are kind of sentences like when you read it, when you hear it, it makes you kind of tired. So I'm going to just skip this and then go to more like a diagram way of explaining. So you remember this is like a build a prediction model. So you have the data, you use the algorithm, and the algorithm find the patterns or relationship in the data and then define it in a form of formula or rules, and that's the model. And then you use the data that you use to build a model, that's called training data, but you give the training data to the model and then have the model to predict. And it sounds kind of weird because, hey, we already have the answer. Why are you predicting? Yeah, but that's weird. But you do that anyway. And then if you do it, then you can actually do is like you can match if the predicted value is matching with the original value, which is like basically the answers. And then there are some differences because the algorithm is not gonna, the model is not gonna give you answer for each row based on the memorizing each answer for the each row. It's instead it based on the pattern, right? So based on the relationship that can be a formula or something, then use the attributes or the predictor variables to give you the answer. So there are some differences in between the predicted value and the original data or like actual values. So that's sort of like expected. Okay. So now here is the thing. It's like so then we can calculate the prediction quality. Each model has a different, each type of the model has a different metric. But let's say like a linear regression case is that average difference between the actual and the predicted variables. Okay, so let's say like we got the quality of like 90, like higher is better and the lower is bad. right? So like we get 90. So and we call this as a baseline. And then from here, what we're going to do is we're going to create another model, this time without the time predictor variable. So like we don't have the time, and instead use the conversion age industry, give that to algorithm, and algorithm find a pattern to build a model. And then give that original data to the model, have the model predict, and get the answers. And once you get the answers, then you make sure you match the answer, the predicted value and original actual values, and then like how the prediction quality is. And it should degrade, right? I mean, like maybe a little bit of the degrade or a big degrade or whatever. It should have a slightly different difference or a big difference. In this case, let's assume like we got like 80. So you remember that previously with all the variables, like age, time, industry, we got 90. Now in this case, we get 80. So we got 10 degrade, right? So without the time variable, the quality of the model degrades for 10 points from the baseline. Okay, so then we give this 10 to the time. Okay, and 10 is not much, not much of a difference, right? But we give time 10 to time. And then the next time, like we're gonna build a model again. This case, like we're gonna remove the age. And by the way, when I say remove, in practice, it's actually not removing, it's actually shuffling the value of the, in this particular case, the age variable. So that even if there is a relationship between the conversion and age and the original data, but by shuffling the values, then we break the relationship. And it shouldn't have any relationship between the conversion and age, because if we don't do it, then we can't actually predict by using original data. So that's why it's using it. But that's kind of like an internal working thing. But it really, the concept-wise, basically we remove the age column and then have the algorithm build a model based on the data, and then give the training data to the model predict, and get the answer, and then matching the answer, predicted values and the actual value, and see like what the quality is. In this case, 70. Okay, and remember the original baseline was 90, right? So in this case, 20 points degraded or decreased. Okay, so without age, then this model performs 20 points worse than the original. So we give 20 to the age. And then last, like in this case, we hide or remove the industry variable and build a model. And the same thing, give the training data and predict and get the answer, and then match the predicted values and actual values. And then it turned out that in this case, prediction quality is 20. The lower is bad, right? So like we degraded a lot compared to the baseline, which used to be like 90 with all the variables. So 70 is that sort of a damage without the industry variable. And this is really the variable importance is. So basically what it is we realize the importance after we've lost them. Okay, I'm sure like you, many of you guys might have had this kind of experience. I have plenty, but it's sort of a kind of a life, right? It's like a variable importance is really about that. I don't know how much of you guys know this band called Beatles, and if I ask you if you happen to know them, and they ask you like who is more important, please write that down in the comment section. And I have my answer, but I'm not going to reveal my answer at this point. And then so how you test them, right? And then it's one way to do it is, okay, the first performance we're going to do like in the same kind of environment, we're going to do like 4 times. And then first time we removed John Lennon, asked him to like take a break, and then had a show without John Lennon. And then how much will the performance degrade? In this case, let's say like the performance means many different things. Let's say like how many customers come, or how many what's the engagement that you see of you observe in the audience. Whatever that can be, let's call it performance. And then like maybe some amount degrade. And the next time we ask Ringo Starr to go somewhere else and have the rest of the members to play. And then the next day, we asked George Harrison to go somewhere else, and then have the rest of the members play. That's basically doing the same thing. And the last is that we don't have the poll, and then how much of the performance degraded. And then the bigger the degrade we had, is that means that person that without that person, we had the biggest degree. That means that person is, supposed to be more important. To me, of course, John Lennon, but this is going to go on forever for, arguments. So I'm not going to start on this, but anyway, so that's how you can basically that's how the variable importance works. Okay, so in exploratory, you build a model, and all you need to do is just, you don't have to do like one by one, like removing or building the model, that kind of stuff. That's behind the scene internally. So all you need to do is you go to the importance tab, and then you get that basically the bar charts that each bar shows the importance of each variable. Okay. Then the next topic is statistical learning variable importance versus coefficient. This is basically like, we get this question a lot. Especially the folks coming from the statistical background ask us, hey, like we have the coefficient chart, and can we use the coefficient to evaluate the importance of the variables? And you can in certain case, but there's some problem. So what the coefficient chart, right? So here's all the diagram or all the prediction models, and the coefficient, you can find those only for statistical learning model. So you don't even have this for the machine learning model, so you don't even have to worry about it. But if you're using a statistical learning model such as linear regression, then you have that. And then it looks like this. Okay, and this shows how much the target variable's value would change when a given predictor, or in this case, each variable at the x-axis, predictor variable changes for 1 point, let's say, right? And then so it looks like, almost like a higher or super lower, and that means have a more impact. And then any variable, the coefficient is closer to 0, probably less, impact on the target variable. It looks like that, but there's one thing we got to be careful, is because the units of the predictor variables are different. So therefore, the bigger coefficient value don't mean there's stronger relationship with the target variable. So what that means? So 1 point in age, let's say age is a predictor variable, that means 1 year. Then 1 point in job level, this is again employee data, so job level is 1 level. And in this, many companies, let's say it depends like how many levels in the company. Let's imagine like this company has only 4 levels or something like that. Then maybe it takes 5 years to move up to the next level, right? So it's not fair to compare the impact of the 1 point change in job level and 1 point change in age, because unit is different. And it makes it even more complicated when you have the categorical variables, such as in this case, job role. This person changed the job from executive to sales rep, or vice versa, or the difference between these two jobs. And that's like, I don't even know like how to compare with age, or difference in the age, or difference in the job level. Okay, sometimes happen, the gender, sometimes happen the country. So those categorical variables can be also tricky too. So if it's only numerical, sometimes you can do the standardized numbers. So therefore, like based on the variance, you can still compare. Yes, you can, but the moment you start bringing a categorical, it makes harder to compare between the variables in terms of like which variables are more important to predict the target variable. So therefore, it's better to use the variable importance. And if that's the purpose, that's what you want to know, then I recommend using that variable importance. Okay, and then don't use a coefficient. That's always kind of tricky or confusing. Okay, so next topic is statistical learning, significance of relationship. Okay, so when you have the importance view, and then when you're using the statistical learning model, such as logistic regression, linear regression, and so on, then you see some of the bars in the gray color. And this shows those variables are not significant. Okay, so what does that mean? In a nutshell, those are not really, don't have the significant relationship with the target variable in a reproducible way. So this particular data, it might look like there is something to do. Yes, there seems to be some kind of relationship, but this is a kind of small relationship, and then probably like when you change the data, when you get the new type of data, even though it has a similar pattern, but then you can't reproduce that relationship. That's really not significant. But what it is, what really is here is actually it can be more than that. So the famous quote from Ralph Waldo Emerson, which is like an American philosopher, shallow men believe in luck or in circumstance, and strong men believe in cause and effect. So when you have some chart like this, right? So the May, June, July at the x-axis, and the number of the shark attacks increase. Just imagine like this is California or Florida or something, and then amount of the ice cream sold also increased from May, June, July. Okay, and when you see something like this, oh, okay, so looks like the relationship between these two. So the more ice cream you sell, the more shark attacks, or vice versa. More shark attacks you have, then somehow like the more ice cream you can sell. But of course, the common sense, it's not. And it turned out what is really happening is the temperature or like a, weather or something. So when it becomes hot, then that shark is kind of like swimming towards the shore or whatever, but more people go into the water, so more chance to get attacked by the shark, right? But also the ice cream, of course, like when it becomes hot, then more people want to eat more ice cream. So we are just looking at the result of something that caused by the being hot, but then looks like because there's a correlation between the shark attack and ice cream sales, and we think I'm sure like we don't, but it looks like there's a relationship. So these types of things is called confounding. And then, when you build a hypothesis about sort of causal relationship, then you gotta check this kind of stuff, right? So in this particular case, a few slides back, we build a logistic regression model to predict employees' attrition. We got the employee data and all the employee attributes such as age, marital status, and also another one is called stock option level. Like what's the level of the stock option each employee get? Okay, and then the stock option is kind of towards the right, but also the gray color. So why is that? And then when you look at the data. Stock option and attrition has a actual relationship. And then marital status and attrition has a relationship. In this case, it's like higher the stock option level, then the less the attrition. And then marital status, depends on which marital status. Let's say single, married, divorced, and so on. And then maybe single person has more attrition. More people left the company, or single people rather than the married people, for example. So in this case, like, there's a relationship, but somehow the stock option is in a gray color. It's called not significant. So not significant has a two meaning, right? So the one is that change is very small. The relationship is very small. Therefore, it's kind of meaningless or marginal. So that makes the variable gray color too. But also another time like the variable can become gray is this kind of case. So like when you see, it's actually stock option attrition. When you look at those two, there's a relationship. But somehow when you build this kind of model, and then stock option becomes gray. So this kind of analysis is called multivariate analysis. So then like I look at the relationship between the stock option and the marital status. Okay, and the x-axis is the marital status: single, married, and divorced. And then the color is indicating the stock option level. So the lighter the blue shows the less level and the lower level of the stock option, meaning zero, meaning there's no stock option. And then the darker the blue is the higher the level of the stock option. And then when you look at the left-hand side, the single bar is basically all the people is actually zero. Single folks not getting the stock option in this company. And then the married is you still have like a zero, but you start seeing like 1, 2, and 3, and somehow divorce for folks get more stock option, the higher stock option level. So it's kind of interesting relationship, but there is a relationship between the marital status and stock option. Okay, and then so this makes it harder. So this brings some kind of drama because same thing happened with that ice cream and shark situation. So we don't know what is actually really causing. So right. So for example, maybe the stock option is the one that people are really care when they think about leaving a company or quitting a company or not quitting a company. And happen to be that like a stock option lower, people tend to leave the company because hey, they're not happy, and then those people happen to be single. So looks like okay, the marital status actually has something to do with attrition, but it's that's actually the result that caused by stock option. You can also argue that different way that no, marital status is actually something to do with attrition, and then the single folks is more free. They don't have families. They don't have to worry about like what do you call it, like a real estate or housing loan and kids and so on. So therefore they tend to leave easier. And then those folks, single folks, happen to be in the lower bucket of the stock option or something. So when you look at the stock option attrition, it looks like there's a relationship, but actually the marital status is the one that's driving. So how can we address this problem? Like, because we want, at the end of the day, we want to know is what is causing attrition, or what is the real relationship, and what is the result of other relationship. And to do is you can actually hold one of the variable uh, constant, meaning let's say the marital status. Okay, let's pick only the married people, married employee. And then there are in that group some folks maybe like a stock option one, some folks step option two. Then let's observe if the attrition changes, right? And in that case, then maybe when the stock option change from 1 to 2 and the attrition, the probability of like leaving the company change, then that means okay, the stock option has something to do with attrition, right? And you can do the other way too. Let's keep constant, keep the stock option constant, as they said, like just keep the only one, stock option level one people or two people, right? All the people in the same stock option level. And then within that group, I'm sure there's some people like single, some people marry, some people divorce. And in that case, I mean, there is a difference in terms of the attrition or the probability of leaving a company. And if there is, then that means, okay, at least marital status and attrition have a relationship without stock option, right? So you can kind of start narrowing down like which relationship is the real relationship compared to the result of other relationship. And this kind of analysis you can do with a statistical learning model, but not with a machine learning model. Um, and then therefore, you see when you open this importance, variable importance bar chart, then you see this gray color or blue color. And the gray color means, okay, that is, for example, but this particular case, the stock option is gray because there is a marital status is actually, so marital status is the same, or like in this case, all the other variables values are constant. And when you change only the stock option level, and then the attrition, the probability of attrition still changes or not. And the answer is no, it doesn't change. That's why it's gray. Um, and then on the other hand, when you have all the other variable, including the stock option, to be constant, and then when you change only the marital status from single to married or whatever, then does that probability of the attrition change or leaving the company change? And it changes. So therefore, it is blue color for the marital status. Okay. Then now, like let's say like, if we remove the marital status from the predictor variable and then rebuild the model. So in this case, we have a stock option and all the other variables, but we don't have the marital status, and then build the prediction model, and then um, see like how that affects on the probability of that leaving the company. And it turned out stock option now comes at number 3 without marital status. So so this is the kind of thing that you can do with a statistical learning model. Particularly, it's called multivariate analysis, and it's really useful when you want to investigate sort of like a causal relationship as opposed to the correlation relationship. Okay. So the last topic is the random forest Boruta for variable importance. So random forest, let me just give you the quick introduction of the random forest. The forest is a bunch of trees. So what is a tree in this machine learning context is called decision tree. Decision tree is really about it creates a series of questions to separate data into multiple groups so that each group will have similar values. Then you can actually, basically each question becomes the rules, and this set of rules is the model, as opposed to statistical learning model tend to have like a formula. But this kind of machine learning model tend to have this kind of rules. Okay, and then in Exploratory, you build a model, you see literally that you see that tree and visualize. And then the forest is basically a bunch of trees. Okay, so like you create a bunch of decision trees. And then to do, you have the original data set, and then you sample, and let's say like 20 different sample data from the original data. And then you build the decision tree for each sample data. And then you get the result from each decision tree, and each decision tree has a different, might give you different answers. So then at the end, you take like mean or majority voting to get the result. That's really the random forest. So you have the data, again, the employee data, and then you have the target variable, which is attrition, the employee left the company or not. And then you take the sample. In this case, the sample usually means the rows, right? So like you have like, hey, row 1, row 5, row 11, or something like that. But in this case, not only sampling the rows, but also sampling the columns as well. And then, therefore, each data set is slightly different. And then, but you build a decision tree anyway. And then, so therefore, this is kind of called like weak tree or weak decision tree. So each tree have seen only the particular subset of the data. So therefore, the tree itself, that particular tree itself, is not as powerful as the decision tree against the whole data. But nonetheless, like you create this, let's say like 20 different trees. You can adjust like how many trees you can build. And then therefore, like each tree is slightly different. Therefore, like you get a slightly different result. And then you have to take the mean or majority value to get the result. Well, it turned out this is kind of a way of building a model. It's called ensemble learning. What it is really like create a bunch of decision trees and then get the result as a whole. XGBoost is also similar, a different way of doing it, but similar in a sense of like building a bunch of decision trees internally. Okay, and then you get the variable importance. The problem of this, for particularly the random forest, is that do all the predictor variables have meaningful effects on the target variable? Maybe some of the variables have nothing to do with it. Unlike statistical model, so we don't know like which variables are really meaningful or not for the machine learning model. And another thing is this is actually sometimes bugs many folks when they see it, is that because of the randomness of that random forest, the variable importance might be different every time you run the model. As you remember, so the random forest takes the random like sampling from the original data. When it does the sampling, it uses something called random. I forgot the name of the particular method, but you actually do the random sampling, right? So you generate you let the computer generate whatever the random numbers, and then use the numbers to get the rows and the columns, and then that's your sample data. So this randomness is so therefore like every time you don't control how you generate the random numbers, like you get the slightly different sampling data every single time. In exploratory, we set the random seed is one or whatever the particular value. So every time you run, you get the same result. But if you don't set the seed, if you let the random samplings really go wild, then like you get slightly different result every time. So you get the decision tree, and then you at the end you get, let's say, like random seed happen to be one, and then you get this result, and then like you run again, and if you don't control the random seed, you get the different result. Different result meaning it's like when you have like a very very strong variable meaning a strong more importance in terms of predicting a particular target variable, then that itself is not going to change. Like this view, if the most left-hand side particular variable is huge compared to others. That kind of difference is usually not going to change, but when you look at the second, third, fourth, like kind of similar, that type of the order or the ranking, it can be changed very easily. Okay, so So if there is a randomness in the result, the suggested importance variable might be just by a chance. Then we can test if they are consistently important or not with a statistical test method. That's really the Boruta. So in order to address those problems, we can use this Boruta thing. So in the exploratory, you can turn on the enable Boruta to yes, and then you get the result. Okay. And then let me see. Okay. And then you get this kind of box plot chart. And then what it really is doing behind the scene is it builds a random forest model 20 times. This is a default. You can control it. Like you want to build like 100 times, you can do that as well. But let's say like that go by the default and then 20 times, right? And then that means that will generate 20 outputs, 20 results of the importance variable importance. Therefore, you can actually visualize by using out box plot the distribution of the 20 different values. So for example, in this case, the most left-hand side is over time, that's the predictor variable. And then sometimes, the score is like, by the way, this score doesn't really mean anything. It's not like 1 to 100 or anything like that. So it's just a relative scale. So number 8 doesn't really mean anything, particularly here. But in this scenario, like variable importance, like we run 20 times, and then sometimes over time is like 6, sometimes like 7, sometimes 5, or something like that. And the next one, the total working years, sometimes like 6, sometimes 4, and it's different values. But then it visualized by box plot. So like we are looking at the distribution. And then like you see, forget about the color for now, but when you see the distribution itself, you can see like how the ranking or the order can be different, every time you run it. Because for especially the second from the left and the third and fourth, kind of like a similar, right? So this is sorted from the left to the right by using the medium, but if you keep running easily, the order can be changed. Okay, but by looking at this way, so it's even like if you get the randomness comes in, but you can still compare which variable tend to be more importance, right? But also another thing is really cool is you can see which variables are useful for predicting a target variable or not by using the statistical test, which is super crazy because this is machine learning. Random forest is machine learning, but we actually use this Boruta method which basically does statistical tests behind the scene by using those 20 samples. I mean, because we build a random forest 20 times. And so when you see the green color, so the statistical test being done, and because of the time, we don't have enough time. So I'm not going to be able to go into the detail of how the Boruta does a statistical test. But I put that slide anyway. So like I'm going to publish that slide later. And if you're interested in, you can take a look at that slide for that this Boruta section. Okay, but what it is like when you see the green color, it's confirmed. That means these are the consistently show the good performance, good good scores, um, in order to predict, in this case, employee attrition. Okay. And the next one, the yellow, this is not confirmed. That means we can't say like if these are really useful to predict the attrition or not useful. We don't know. And in the statistical world, we don't know, meaning usually like we don't have enough data to say these are significant or not. Okay, so these are the one like you kind of like want to suspicious about, but that doesn't mean these are not useful. So we just you don't have enough data to back up. That means compared to green colored variables, these are kind of less important, but not only less important. So like you want to start with the green colored, and then like next, and then you want to move on to the yellow variables. The last one is a gray color. These are confirmed as not useful. So these variables, based on the statistical test, they consistently perform that, showing that it's not really useful to predict the attrition in this particular case. Okay. And then, like I said, I put like some slides to explain how the Boruta works. And if you're interested, please take a look at it. And then, okay, okay. So that's how you can use this view by turning on this particular thing. So like, I'm going to just show you quickly. So like here's a employee attrition data. So like you have the data, each row is an employee, and I have the summary view was displaying. But I'm going to go to the analytics view, and then let's say I'm going to build a random forest model or something. And then target variable, I want to select the attrition, right? And then predictor variable, maybe like I'm going to include all of them. But also, I actually know, for example, this job role and the department is kind of similar information. So I'm going to remove some information. And then like, let's say like build a model. And then it's, super simple model I just created. And then like that one like I was talking about here is importance. So by looking at this chart, you can judge which variables are more important to predict in this case attrition. And the more important means basically have a stronger relationship with attrition. Right. And then the one like I was talking about, the Boruta, is like under the property, you go here, and then there is a variable importance section that enable Boruta. So if I select yes, so this is crazy because the random forest itself, create 20 by default create 20 sample data from this data, and then build 20 decision trees, right? So that itself is like a crazy amount of like a processing happening. Maybe I shouldn't say crazy in this day and age, but has a bunch of trees, and then on top of that, this by enabling this Boruta, it repeats that process 20 times. Okay, so that's what it's going to do. So it takes a little time. This data set I'm using here is a small data, so it shouldn't, but when you have the bigger data, it might take a longer time. And then this is I was talking about. So like this basically, you just imagine you have a 20 variable importance bar chart, and then it's slightly different values, right? So like you use the box plot to show the distribution, and that's what we are looking at here. And then if I were you, then I would go, okay, maybe like over time to age, these 4 variables seems like have stronger relationships with attrition. And then maybe like I'm going to visualize this and how that relationship is by going to the prediction tab and then see, investigate further and so on. Okay, so that's really in a nutshell of the variable importance of today's seminar. So let's summarize this. The model is really a definition of a pattern that algorithm has captured in the data. When I say the pattern, it's really the relationship among the variables. Okay, and then the prediction model is not only for prediction itself, but you can gain a lot of insights about the relationship in that data. So, and then like, you can use analytics grammar to have the common framework to understand the such relationship and patterns in the data that those algorithms have found. And then one of them is called variable importance. And then that's what we cover today. And then you can see, you can go to the importance tab to compare which variables are more important or which variables have a stronger relationship with the target variable. And then sometimes when you see the gray, that means it's not significant. And it can be the amount of relationship, degree of the relationship is so tiny, that's why it's gray, or because some other variables have the real relationship with the target variable. That's why this gray variable itself doesn't have much relationship by itself. Okay, so that's it for today. So the next seminar is next week. I'm traveling, so I'm gonna skip. But the week after next week, July 21st, I'm going to introduce the exploratory server, the cloud and the collaboration server, and what you can do by using the exploratory server stuff. Okay, and then for the future seminar or the past recording, you can go to our website, exploratory.io. Under the Learn, there is an online seminar menu, and then this will navigate you to the online seminar page. Then you can get to the past recording or future information as well. Okay, that's it for today. And then with that, I'd like to open for the question.